Hello, Ralph. Can you hear me?
Yes, I can hear you. So who is that?
It's Marius. Hello.
Hi, Marius.
I'm Marius. I will be the chairman this afternoon.
Oh, okay, you're the chairman. Yeah, should I try to share my screen?
Yes, you can. You can indeed go ahead for sharing the screen.
Okay, let me try. I think you need to give me co-host permission or something. Yeah. So can you see something? Can you see my slides? Hello, anybody out there?
We can see the slides.
Okay, you can see the slides. Very good.
Maybe you try moving slides so that we can check if it works. It's fine.
Okay, good. Sorry.
All right. So maybe we can start this afternoon session. Let me talk to the audience as well. So there will be 4 talks this afternoon. Originally, there were 3 talks online. We will have 3 talks online plus 1 talk face-to-face, with a little break between 2 plus 2. So we are expecting to hopefully finish around 6:30. And there is a reception at 8 o'clock. So here, well, in Montero, not in this room, as far as understood, it's in the palace, correct? In front of the palace, which is this building which is standing over there. All right, so these are the last changes with respect to what is written in the web page. All right. All right, so Ralph, this was not exactly for you, unfortunately.
Yeah, unfortunately.
You won't be able to join the reception, but you can now talk. So Ralph Blumenhagen from Max Planck in Munich is our next speaker on quantum breaking in the high energy phase of, I suppose, quantum gravity.
Yeah, quantum gravity, that's true. Thank you very much, Marius, for this introduction. Yeah, indeed, unfortunately, I cannot be in Corfu this year, but given the nice weather we have here in Germany over the last days, I can easily imagine sitting at the seashore in Corfu and these nice outdoor restaurants and so on. Okay, so today I will nevertheless deliver a talk to you, as Marius was saying, on quantum breaking. And this is based on 2 papers that we wrote during the last year. So the first one, it was 2 students from Munich, Christian Kneißl and Adriana Macridou. And the second shorter one is with 2 additional students, Rafael Alvarez Garcia and Lorenz Schlechter, and appeared recently. So this morning by Thomas, we heard already an introduction to the General Swampland program and focusing indeed on de Sitter construction. And this is also where this talk is sort of located in subject-wise. And it's also related to some of the things that Thomas was only mentioning very briefly, so that on this point then I can extend a bit more. So let me just start more generally. So guided by general quantum gravity arguments and experience from string theory. Okay, so the swampland program is guided by general quantum gravity arguments and experience from string theory. And of course, string theory, we are not sure that we completely understand it, yes. So we are definitely looking in certain backgrounds that we think we well understand. So we are facing what might be called a lamppost problem here. Of course, it's always, we are heading for more general arguments to support our swampland conjectures. And during the last 3 or 4 years, we have now a couple of conjectures. So this is always in the form of conjectures. Just to name a few, one that also Thomas mentioned, I think the swampland distance conjecture, the de Sitter swampland conjecture, and the ADS distance conjecture. And these have mostly evidence from perturbative string theory constructions. And it's a viable question, certainly, to ask whether they also hold non-perturbatively, so more deep inside the moduli space, or in other extreme situations. And here I have in mind, in particular, the so far still unknown high energy phase of string theory, where we have no true idea, I would say, to what this high energy phase actually is made of, and what are the new degrees of freedom coming up here. So there were suggestions that this is related to a topological field theory or an extension thereof. In particular, Kumrum was making this point. So we will see. Yeah, so let me just review to make it self-contained a couple of swampland conjectures that we need for this talk. So first there is the de Sitter swampland conjecture, and there's a refined version, but for this talk, this is not really necessary. So this says that the gradient of the potential is always larger than an order 1 number times the potential. And this apparently forbids de Sitter minima. So eternal de Sitter would not be a solution of quantum gravity if this conjecture is true. So it has to decay after a certain time, or just gives you sort of a quintessence kind of realization of a quasi-de Sitter space. And we have heard from Thomas that there's also this trans-Planckian censorship conjecture, which is a bit weaker, well, which is essentially weaker, and only reproduces the de Sitter swampland conjecture in the asymptotic field limit. On the other side, I think this was not mentioned by Thomas, there was a proposal, maybe not yet a conjecture, but you can look for the condition when eternal inflation can happen, and then require that eternal inflation should not be allowed to happen. And if you work out the details, as was done by Tom Rodelius, you find that this imposes a weaker constraint than the de Sitter swampland conjecture, where on the right-hand side, say in the n dimensions, space-time dimensions, there is not an order 1 number, there is still the potential appearing to some power. And so this is in natural units, so Planck scale is order 1. So V is always, we think of V as being smaller than 1. So this is a number smaller than 1 appearing on the right-hand side. And there was a paper also by the Harvard group. And what they were showing in a nice way is that they applied this sort of non-local TCC conjecture to a sequence of de Sitter bubble, non-perturbative bubble decays, and they were showing that this could lead to an effective potential that marginally satisfies this bound. So in other words, you could think of the TCC as admitting a constraints which is more of this type here, of the no eternal inflation bound than the de Sitter swampland conjecture in general. Okay, so this brings me to this other approach called quantum breaking. So here, this is an approach put forward by my colleague Diadvali and his collaborators and his group, Theda Gomez in particular. And here they have a slightly different point of view. And as Thomas was saying, so they were not thinking about the full or 10-dimensional theory. They were just looking at quantum aspects of 4-dimensional quantum gravity, so to say. And even there, they are claiming that they found, so to say, an inconsistency or mechanism that forbids eternal de Sitter spaces. I cannot repeat their approach, and this is also not important here. I'll just tell you now. So what they did is they viewed de Sitter space as a coherent state of gravitons. So Pia has this corpuscular theory of quantum gravity. Coherent state over Minkowski space. And then this state, in this coherent state, it decoheres. So by scattering of gravitons from the state, and they were estimating the break time, so the medium time when this, so to say, state decays, say by a factor of 1/2 as a medium time. So this leads to a quantum break time that is of the following order, scales in the following way in n dimensions. So m Planck to the power n-2 over h to the power n-1, and so this is old result, so to say, and when this de Sitter swampling conjecture came up, that they could turn this, so to say, into a conjecture by saying, so for them, this is a fact, yeah. So this is just a fact of quantum gravity, if you believe their arguments, so they turn it into a conjecture, or a proposal that this is a quantum effect, but this quantum effect should never play the leading role. So that should be censored by a classical mechanism that even leads to a faster decay. And here these rolling fields again come into play as being this mechanism. And when you make the estimate, then you find precisely, if you have this bound here on the quantum break time, that for a slowly varying field, this leads immediately to the no eternal inflation bound. So the quantum break time bound is the same as the no eternal inflation bound. Is the same, roughly speaking, as the TCC bound. Yeah. So what we were just asking a naive question that lead us some way, so to say, in a chain of arguments then. So what we were asking a year ago, more or less, so we were asking whether one can also get the de Sitter swampling bound, the original one. Does it show up in this approach of quantum breaking as well? The answer is not. So the answer to that is essentially this paper. And so what we were doing, this paper was based on a different approach, not Gia's approach to quantum breaking. There was a different proposal that there's another mechanism that is sort of equivalent and gives you the same quantum break time. And that was proposed by Tomi Markkanen also a couple of years ago. Then we're publishing this paper, so we got some critical reaction, in particular from the author of this paper, claiming that there's a certain aspect, at least in this paper, that is not 100% correct. And just to cut a long story short, after a big back and forth discussions, so we agreed to that point, to that criticism. So this is why I deliver now this talk in a slightly different way than you might have heard it on different conferences. So now we have a slight change, so to say, of paradigm, but the main conclusion will be the same. So let me explain my point. This is now the contents essentially of the first part of this talk. Okay, so what we usually do, so we are just four-dimensional quantum gravity, and then so the quasi-classical approach in which we only quantize fields, say a classical field, so a scalar field on still a classical curved de Sitter background. This is the framework we are in. So gravity is not truly quantized yet. And then one can define, as you might know, this Bunch-Davis vacuum, the thermal vacuum. And usually you use the usual FLRW, Robertson-Walker metric, and these coordinates of an expanding universe. And when you do that after computation, so you quantize, so this is quantum field theory, you define your vacuum, and then you compute in your vacuum the vacuum expectation value of the energy momentum tensor of the scalar field. Of course, it's divergent, so you have to renormalize this. There's adiabatic regularization coming in. So that's a longer story, and there are textbooks on that. And what you nicely eventually find is that this renormalized energy momentum tensor is proportional to the de Sitter metric. People say it preserves the de Sitter isometries. Yeah. On the other hand, it's known for a long time also that if you go to another system, so if you describe your de Sitter space such that it's time independent and that your horizon, there's this de Sitter horizon, of course, becomes explicitly visible in the metric, and the metric diverges there, this is the so-called static patch. If you do a similar computation in that patch, and often you can relate this result, by the way, to the result, in particular in 2 dimensions, you can relate this result to the result that you have obtained in Robertson-Walker metric, because there's just a conformal transformation between the two if you have a conformal theory. So it's 100% fixed. And if you do that, and you now compute the vacuum expectation value of the energy momentum tensor in this patch, you find that it's not just proportional to the metric. There is again a part proportional to the metric, and this is already dictated by the conformal anomaly. But there's another part that more looks like a contribution of a free, of a relativistic scalar field. Yeah, so of a gas, relativistic gas. Here's a 4-dimensional result. But it shows this has also a singularity at the horizon. Okay, moreover, in the course of the computation, you can find that this prefactor here has this nice thermal interpretation. So it's given by this, what we call a flat space thermal integral. No? So it's just flat momentum space where you integrate over, and it's the Boltzmann distribution. And this is the energy density of a Boltzmann distribution in a free gas of massless particles. And you find precisely this number. So this is this point of view that in the static patch, you see this thermal radiation coming from the horizon, and it's time independent. So there's this steady inflow. At the same time, the universe expands and redshifts this energy so that you get a static situation. So far, so good. I think there's no doubt about it. And by the way, there were similar results obtained a long time ago, also in Minkowski space, where you also have this Rindler coordinates when you are in an accelerated system. Okay, so what do these quasi-classical results tell us about quantum gravity, and how is this related maybe to string theory? That's of course completely unclear a priori. So the natural next step would be to say, okay, I have this quantum matter contribution, and usually whatever I compute, if I do gravity, and I have an energy momentum tensor, I plug it on the right-hand side of my Einstein equation. And this is what we often do also in string theory. When we do modular stabilization, we compute the one loop contribution, the one loop cosmology constant. It's modular dependent. We put it on the right-hand side of our Einstein equation, look for back reaction. So here you should actually do the same. But if you do this, you run into a slight problem, because these 2 different ways of quantizing the field leads to 2 different results. So if you do it in Robertson-Walker coordinates, that is, I think, generally accepted, as said, so you find something that's proportional to the metric. So as you can see, it can be essentially absorbed in a redefinition of the cosmological constant. So the system, this is, of course, usually smaller than that, this contribution. So the system will adjust, yeah, slightly change and adjust to this additional quantum contribution. On the other hand, if you have this additional piece that was not proportional to the metric in your quantum contribution here, which more contributes like matter, then just eternal de Sitter is not any longer a consistent solution to this Einstein equation. So there seems to be a paradox. So both observers seem to predict qualitatively different evolutions of the initial de Sitter space time. So how could this be resolved? Well, I think there was a long discussion in the past, I think, which I am not know in all detail, to be honest. But when you see in textbooks, I mean, some people, I think, say that this quantum energy momentum tensor in the static patch might not be physically reasonable. Yeah, because as you can see, because it has these explicit singularities at the de Sitter horizon, so something might not be quite right with this inertia system. Well, on the other hand, you could also say, well, but as long as I stay away from the horizon, and I might expect quantum gravity effects that I have not captured to be relevant at the horizon anyway, why is not the result, at least in the center of the static patch, correct or trustable? And what we claim is, so to say, or suggest that there is another way, in view of the swampland conjectures, there's another way of interpreting or resolving this paradox. So, because if we now follow essentially Dwali's idea, so and censor that, so to say, that we say on the right-hand side, so before we had a classical cosmological constant, and we had a quantum energy momentum tensor that could change this and redefines it. So the resolution lies in the idea that we also add a classical contribution for the energy momentum tensor that is also not proportional to the matrix, so comes, for instance, from a rolling field. Yeah? So that then this quantum contribution again gives only a slight change of this classical already present contribution, which of course means that de Sitter vacuum could not be possible from the very beginning. Yeah? So there is this second resolution, and okay, this is the idea. And if you now make it more quantitative and you say require, following Dwali-Gomez, that the quantum correction should be smaller than the classical rolling field contribution. Yeah? So the quantum contribution scales like h to the n, because it's coming from this free gas in n dimensions. And if you do the math and transform it, so to say, into a break time, so if you have a rolling field, the break time is 1 over h times epsilon. For epsilon, you have this general formula, blah, blah, blah. So you plug everything in, you find it precisely the quantum break time of Dwali and Gomez. I think this is encouraging, at least to say the least, to say that this might not be a completely stupid idea. Yeah, so that this new resolution of this paradox, or that the existence of this paradox in the first place, points towards quantum breaking and an inherent instability of n-dimensional de Sitter space, independent of how you realize it by extra dimensions and stuff. So that's our working hypothesis. Not a proof, completely clear, but it's an idea. At least we should follow and see what the consequences are. So this is our proposal. The matter contribution being proportional to the matter, the matter contribution you see in the static pledge is physically reasonable and is a manifestation of quantum breaking of de Sitter space. And what we have shown in the paper also is that even in non-conformal case, so the conformal case is the easiest one because they have conformal anomaly. You can really precisely fix everything and also relate the two by conformal transformation, which is anomalous, of course, in this case. But even if you are in the non-conformal case, what we find is that it is essentially given the contribution by a UV contribution, and this is given by the terminal flat space Boltzmann type integral. So there is a terminal contribution, the main contribution, in particular, if you are only interested in the scaling with h, you can read off from this terminal flat space Boltzmann integral. That's our proposal.
Ralph, you've got 10 minutes left.
Excuse me? 10 minutes, okay. Yeah, I might not go through everything, but don't worry. That's perfectly fine. So what we did then is, okay, there's one immediate consequence, so that we didn't mention in the first version of the paper, but which is now clear, because now we have the same situation for Minkowski, and there we have Rindler coordinates as opposed to flat Minkowski coordinates. And if we claim in the de Sitter case, and also in the Rindler case, you have the same kind of story, so there will also be a matter contribution to the quantum energy momentum tensor. So you are led to the proposal automatically that also, at least non-SUSY, here we are just looking at a scalar field on Minkowski space now, that at least non-SUSY Minkowski vacua are not solutions of quantum gravity either. This might kind of completely stupid proposal, but maybe not, because in string theory, we have also very hard time to control really, if you have a low degree of supersymmetry, to control pure Minkowski minima. I would say a Minkowski minimum is a very special, really tuned situation where it happens to be that the cosmological constant is 0, but because it can be negative. Now we know that there are in general anti-de Sitter minima. And this point was raised also in a paper by Palti, Waffa, and Weigand recently, where they were looking at instanton corrections for non-supersymmetric and n=1 supersymmetric string constructions, and more or less without supersymmetry, higher supersymmetry, we're finding that the minima are often destabilized. So it's very hard to say that you are sitting with all these non-perturbative corrections, that you are sitting in a stable eternal Minkowski minimum. So that's a claim, yeah, not more, but a consequence. But it's an immediate consequence of the proposal that we are doing. What we were actually doing in the paper then was to generalize the situation to string theory. So running the same story for string theory. And so we were computing then terminal flat space matter contributions and computing them via string theory methods. Because we can also put string theory at finite temperature and compute the terminal partition function and read off the energy density and so on. And look how it scales with the Hubble scale. and then see about the temperature. Temperature is identified with the Hubble scale and how it scales, and then evaluate what is the quantum break time. So the new issue that appears in string theory is, of course, the Hagedorn transition. So there's a critical temperature, which is of the order of the string scale. And the belief is that beyond that temperature, it's not a final temperature, so to say, the end of the temperature scale. You can go beyond, but beyond there is a sort of new phase of string theory. This was proposed by Attic and Witten again many years ago. But not very much is known about this new phase of string theory at very high, ultra high energies. And so there were proposals, but I cannot really evaluate how good and based they are, so that it might be a subcritical string theory or a lattice theory or a topological gravity theory, like in this more recent proposal by Agrawal, Gukov, Obiet, and Waffer, who were making the statement that in the early phase of the universe, we are in this very ultra high energy phase of string theory, and we are sitting in sort of a topological gravity theory. That was their assumption, and they were seeing how far this could be used as, so to say, the initial conditions of our universe and to explain the things that are usually explained by inflation. Okay, so there's motivation for that, for this question. And here now I keep the story short because I've given this talk many times, and this part hasn't changed. The main new thing is that Attic and Witten argue that the extrapolation of the one loop free energy to temperatures higher than the Hagedorn temperature, independent of the dimension in which you are, always scales like t squared. That's always a quadratic scaling. So there is a decrease in the number of degrees of freedom when you cross the Hagedorn transition. And as a consequence, so it scales like t squared. So what you see effectively is a two-dimensional behavior. And of course, this is also what we find if we compute the free energy of the string. And so following Waffer's and friends' notation, so we call the high energy phase phase one. This is where our universe started, according to their picture. And the low energy phase, so energies below M string, temperatures below M string, phase two. And indeed, in phase two, we just find the familiar results that the field theory results that the quantum break time scales like in the no eternal inflation bound. And in the high energy phase, due to the scaling here, it scales like effectively a two-dimensional theory. And this means that it scales like 1/h. Here, because it's a one loop contribution, there's also a factor of the string coupling square in the denominator. Even though Attic Witten claimed that in the true theory, so to say, not in this naive extrapolation where you now keep the tachyon and you just ignore it, so it's not a honest, fully honest computation, there would even be a tree-level contribution. And this would mean that this factor GS would be gone. But you precisely find here the bound of if you ignore GS for the moment, you find in phase one, you always, independent of the dimension, you find the bound from the initial de Sitter swampland conjecture. And this is what our idea was, to see how it can come up from quantum breaking. Here now quantum breaking interpreted in the way that I explained in the first part of the talk, following the Markham's approach. Okay, so I have not much time, I think. How many minutes? 3?
2 minutes.
What did you say?
I was saying that you have still 2 minutes left.
2 minutes, yeah, okay. Then I'm not talking very much about the second paper, just maybe the idea. So here, so we have this proposal that in the high energy phase, high temperature phase, the quantum break time should scale like 1/h, independent of the dimension. So we were looking at least that whether we can identify in the literature at least a toy model, so to say, where a bit is known about this high energy phase, where we could do an actual honest computation in this new phase. Of course, for general string theories, the new phase is not known, but there were proposals for two-dimensional non-critical strings, where actually tachyon in this case becomes massless. And there were proposals that for type 0 string theories, for instance, in 2 dimensions, the theory can be exactly solved in terms of a matrix model. So you have a matrix model description, both at small and at high temperature, if you impose a T-duality here, terminal T-duality. And there's even sort of an M-theory uplift of this type 0, non-critical type 0 theories. And this was defined in these papers by Horava and Keeler. And this is defined by a non-relativistic Fermi limit in 3 dimensions. So the details are not important here, but it's in 3 dimensions. That's important. So we would like to see if we compute now, whether we can compute, have an idea of computing the quantum break time in this 3D theory. And there was a proposal for the effective theory also of this non-relativistic Fermi limit in the ground state. And this is essentially given by a higher Spin-Chern-Simons theory, where the lowest lying mode, so to say, gives you conformal gravity. So it's not Einstein gravity in 3 dimensions, which is also topological, but conformal gravity by Witten. And so we were using this theory and test some of the swampland conjectures. And we could find, indeed, we find confirmation. We were checking, I'm not going, this I skip now, but we were finding confirmation in particular of the ADS distance conjecture here, where the tower of states becoming massless when the cosmological constant goes to 0. Here we have a 3-dimensional theory, so there's no tower of string, no Kaluza-Klein modes, but you have this tower of higher spin fields, and the tower of higher spin fields plays the role of this former fields coming from higher dimensions. And for the de Sitter part of the story, we were computing the quantum break time, and what we were seeing is that in this model that we were proposing, the Planck scale was not an independent, it's conformal gravity, so there is no Planck scale. Planck scale, if you get something like a Riemann tensor, it comes from a slight change of your action, and so that the Planck scale is given by, is again given by proportional to h. So that in your general formula for the quantum break time, 1 factor of h cancels out and you get 1 over h. So that's just the story in short. And of course, unfortunately, I don't have time to explain this in more detail, but we see a way here how a mechanism can be at work that for this 3-dimensional, almost topological theory, nevertheless gives you a quantum break time that scales like 1 over h and not like m Planck over h squared. So all this is consistent with our claim, and this is just a small letter that we wrote to support our claim. So I come to my summary, which is short because this was actually the summary of the second part of my talk. So I think the main message is that, so we were making an attempt to give you a new way, say, followed by Markkanen, of how quantum breaking could be interpreted by these different results for the quantum energy momentum tensor for pure de Sitter in the Bunch-Davis vacuum between Robertson-Walker coordinates and static coordinates. And then we were discussing the consequences of that in string theory and finding a proposal that in the high energy physics, in the high energy limit of string theory, you might be able to see a quantum break time that scales like in the de Sitter swampland conjecture. Yeah, I think that's all I have to can tell you today. So yeah, thank you very much for listening.
Thank you, Ralph. Thank you.
Yeah. Questions or
any questions? In the local public?
So I think Emmanuel, Malek.
Oh, there are questions online, maybe. Can you
okay,
check?
this was online probably. This is what I can see.
Should I just go ahead and ask my question, or?
The chairman has to make the decision.
Please go ahead, Emmanuel.
Okay, thanks, Ralph, for the nice talk. I was just trying to follow your the de Sitter argument at the beginning.
Yeah.
Am I right in understanding that essentially you're saying there's an inconsistency with classical de Sitter that comes from a semi-classical consideration?
Yeah.
In 4D, so
absolutely
much stronger than, I guess, the philosophy behind swampland, where the argument normally is that it's some UV completion that will cause problems.
Yeah, indeed, indeed. But this is very much in spirit of also what Vali and Gomez are.
Yes.
Very much. So there is an inherent problem already. So forget about all higher dimensional theory. You have done this, so you arrived at your effective 4-dimensional theory. And even then, you see that internal de Sitter vacuum leads to a quantum inconsistency. That's the proposal.
And it seems to match exactly what you get also from the swampland picture then, though.
Yes, indeed, you get bounds of the same type. In this case, we get the no eternal inflation bound, which scales in the same way also with a number of dimensions. So I find this encouraging, at least, that this idea is not completely off.
Yeah. It just surprised me that
I'm not so
it's a
much
4D.
The expert, as you can imagine, I'm not so much the expert on these old-fashioned quasi-classical computations, but at least for me, as you know, maybe I'm too naive, but for me, I think this is it's quite striking.
Yeah. Okay. Thank you very much.
Yeah, welcome.
All right, thanks. Other questions? Other hands? No? Fotis, yes, please, Foti, go ahead.
Hi. I wanted to ask, if I understood correctly, you are saying that the arguments of quantum breaking that restrict how much a de Sitter can live also apply to 3 dimensions, apparently.
Would also apply to 3 dimensions, you are saying?
No, I am asking, is this because in the end you went fast and I didn't
yeah, well, I mean, of course, the 3 dimensions.
So that would be very interesting because usually, you know, people say 3 dimensions, gravity is.
Yeah, topological. Well, yes, I'm not literally.
It would be great if it applies there also.
Yeah, I'm not literally saying this. I think I'm just extending the no eternal inflation bound also to 3 and 2 dimensions, this formula. But indeed, this is a topological theory, Einstein gravity in 3 dimensions is indeed a topological theory. And indeed, one might be a bit more careful. There are no gravitons. So the argument also of Dwali and the naive argument of Dwali does not apply, because they have this corpuscular theory, so they need gravitons for their argument. So like a black hole or non-trivial objects in gravity are made as bound states of gravitons. There are no ground states, so pure topological gravity might not fit into this scheme. But the theory that we were considering on the other side, this conformal gravity plus extra stuff, there's an extra matter particle. I couldn't go into detail, and this extra matter field makes it non-topological, and then there's 1 degree, and even in so what you get is topological massive gravity, in fact. And in topological massive gravity, it's known that there's still 1 massive degree of freedom. No?
Yes, no, that's interesting because, okay, in any case, if you do a flux compactification to 3 dimensions, there you get extra stuff. So it might mean that in flux compactifications to 3 dimensions, we might expect that there are restrictions in de Sitter.
Yeah.
Or seemingly de Sitter solutions. Oh, thank you.
Yeah, you're welcome.
Thanks. Other comments or questions? All right.
Yep.
Thank you again for a nice talk and discussion.
Okay, then I'm stopping my sharing. We are done.
We will see you next time in Corfu.
Yeah, hopefully next year.
Our next speaker is Severin Luest. Severin, are you around?
Yes, I'm here. However, you have to allow me to share my screen.
Then you will be allowed soon to do whatever is needed. You should now have access and be able to share your screen, Severin.
Okay, are you able to share your screen?
You can see. So again, our next speaker is Severin Luest from Harvard, and the subject of the talk is the Tadpole problem. Please, Severin, go ahead.
Yeah, thank you very much for inviting me here. Of course, it's a pity that I can't be in Corfu in person, but I'm glad that I'm able to give you at least a talk in this format. So what I'm going to tell you is work in collaboration with Josef Behner, Johan Blabak, and Mariana Granja, and I believe most of the material I'm going to cover is from this paper which we put on the archive in March. So I think, as you're all aware of, flux compactification of string theory usually give rise to an enormously big landscape of string theory. In a series of papers, there have been made estimates about the size of this landscape, and that's usually 10 to the very big number. I think the smallest estimates are something around 10 to the 500. And in particular, such a huge number arises because for Calabi-Gauss, with large Hodge numbers and therefore with a large number of cycles, we have many choices of fluxes. And then there, of course, is the obvious question, where in that enormously large landscape do we live? However, even though we have a lot of choices for fluxes, these fluxes are not completely unconstrained. They're not completely arbitrary. First of all, they are integer. They have to obey integer quantization relation. And however, they are also constrained by a so-called Tadpole cancellation condition. And we'll try to argue that these two constraints are actually relatively strong and strongly constrain the vacua which are there within the landscape of vacua. So in other words, an important question is which properties have the consistent vacua satisfying these constraints. And over the past, there appeared a lot of different approaches on studying, on exploring that landscape. Maybe the most obvious one is to try to systematically study the landscape by extensively or random mapping over all, or at least a certain subset of flux configurations. However, since this landscape is so large, usually that's not feasible, and one can only gain sensible information by looking at very special examples, which are usually relatively constrained. A more, maybe a bit more promising approach is the statistical approach, which has followed in a series of papers almost 20 years ago now, where using statistical methods, they arrived estimates on the size of the landscape. Maybe the most natural approach probably for most of us is to get some analytic understanding by exploring, for example, the symmetries and the mathematical structure of the underlying equations and so on. And I believe Thomas and Eric gave a bit more details on this approach in their talk. And related to that approach is also the recent swampland program, which tries to attack the problem in a related but slightly orthogonal way, maybe. However, what I would like to focus on most in my talk is I would call it algorithmical approach, because using modern computer technology, which is nowadays very powerful, we can use modern big data or artificial intelligence or machine learning algorithms to study the landscape, and that's what I would like to focus on here mostly. So machine learning and artificial intelligence applied to string theory problems recently attracted a lot of interest. A nice review can, for example, be found here. And here I would like to focus on a certain subset of algorithms which are inspired by biological evolution and genetics, and therefore also often called evolutionary algorithms. And these can be used to specifically search for or generate string theory vector with very specific properties. And here I would like to use these algorithms to on a special example, to search for flux configurations which have full modular stabilization and see if this gives rise to any interesting constraints. So let me give you a very brief review on flux compactification, maybe on M theory on a Calabi-Yau fourfold, which also gives rise to an F theory setup. And however, this can also be very similar carried over to a type 2B on a Calabi-Yau threefold. So in the M theory action, there's the kinetic form of the four-form field strength. And if we give vacuum expectation value, so-called VAF, to these four-form field strengths, then I observe that this Hodge star actually depends on the Calabi-Yau metric. And therefore, such a term, if I integrate it over the internal space, this can give me a potential for the moduli, and the moduli will be stabilized at the minima of this potential. One can also formulate that in terms of a superpotential formalism. Here, actually, one can write down even two superpotentials of this form. And then a supersymmetric vacuum is given in terms of the F-term equations. And if one simply counts the number of fields and the number of equations, one sees that this is actually just enough equations to stabilize all of these moduli. Here, I would like to focus mostly on the complex structure moduli. However, this approach requires knowledge about these period integrals, and this is in general very difficult. So as I think Thomas also highlighted in his talk, it might be easier to study these problems by other means and not directly look at these F-term equations. So, however, there's an important constraint, namely the Tadpole cancellation condition in M theory and F theory. And this condition states that the integral over G4 by G4 over the internal space has to be the Euler number of the Calabi-Yau fourfold divided by 24. Otherwise, we will not have a consistent vacuum. And of course, we can express the Euler number of a Calabi-Yau fourfold in terms of the Hodge numbers. And if one actually does that carefully, one obtains the following expression in terms of these Hodge numbers. And we see that only H31, the number of complex structure moduli, and H11, the number of Kähler moduli, contribute positively. And here I would like to focus on the regime where H31 is large and the H11 is potentially small. And we see directly that in that regime, the contribution to the Tadpole cancellation condition chi over 24 scales roughly like 1/4 of the complex structure moduli. And now the question is, if we impose flux quantization on that G4 and demand that we find the G4 which gives rise to a nice vacuum where all moduli are stabilized, can this G4 which G4 be fairly small, or does it maybe also necessarily have to scale in some form with H31? And using these considerations, we came up with the following conjecture, which we call the Tadpole conjecture. So assuming that we study F theory on a Calabi-Yau fourfold or general M theory on a Calabi-Yau fourfold, and we study it in the regime where we have a large number of complex structure moduli, which are all stabilized by integer fluxes, and probably should also focus on being at a generic point in moduli space. So maybe that conjecture might break down at very special points in moduli space. Then we conjectured that the charge induced by these fluxes, the flux contribution to the Tadpole cancellation condition also scales linearly with the number of moduli, and alpha being an order 1 constant. So if I go one slide back, we see that on the right-hand side of the equation, scales like 1/4 of the number of moduli. So depending on whether alpha is smaller, equal, or larger than 1/4 of the number of moduli, if this conjecture is satisfied, we might or might not be able to stabilize all of the moduli actually. So one can look at the literature and at examples where when a certain number of moduli have been explicitly studied and explicitly stabilized in various setups. And if one compares these examples with this conjecture, one actually makes the, I find, rather surprising observation that all these examples seem to be compatible with that conjecture, and for all these examples also this proportionality constant seems to be rather relatively in the same range of roughly 0.4 maybe. Let me also comment briefly on more recent examples. So first of all, my collaborators, Joseph, Ariana, together with Calabi, they're studying explicitly F-theory on Calabi fourfolds with a weak Fano base, and they find a good confirmation of the Tadpole conjecture, therefore, for the 7-way modular, but I do not want to say too much on that. However, there was also recently very interesting work on modular stabilization in the large complex structure regime. And the Madrid group published a very interesting paper where they studied very systematically flux complications in the large complex structure regime, including certain corrections. And they found two very explicit scenarios for flux compactification. And the first of their scenarios seems to agree very nicely with this Tadpole conjecture. However, in the second scenario, the charge carried by the fluxes does not seem to scale in general with the number of moduli. So this looks like a counterexample of the Tadpole conjecture. However, a couple of weeks ago, Eric Plauschin put a paper on the archive where he used certain statistical properties of the Kreuzer-Skarke list, here exclusively in a type 2, and they found a very strong scaling of full charge with the number of moduli with an exponent which actually lies in the regime somewhere between 3 and 7, even so the scale which is even stronger than the one conjectured by the Tadpole conjecture. But interesting, if one takes these estimates of these statistical properties of the Kreuzer-Skarke list and uses them to devise the distinct type of scenarios in the Madrid paper more carefully, one finds that there is indeed a scaling with the number of moduli. So this counterexample actually seems to be another example of the Tadpole conjecture. And for more details, I would like to refer you to a note which I put on the F today. And also, I think Thomas, Eric, and Damian will study that problem in much more detail in the upcoming paper, which I believe should appear very soon. So go back to my original problem of studying modular stabilization using modern computer techniques. So as a matter of fact, even though we can easily estimate how the number of how the charge scales with the number of moduli, finding explicit vacuum for many moduli is a very difficult problem, and constructing such vacuum explicitly can be very difficult. So it's a rather natural to try to use big data or AI algorithms to systematically search for flux vacuum, and here to search for flux vacuum which stabilize all moduli, do that at a very generic point in moduli space, and have a charge as small as possible. And the technique we use is so-called differential evolution. And that's a global optimization algorithm inspired by biological evolution or genetics. And the goal of such an algorithm in general is to find the global minimum of a fitness function. So a fitness function is a function which takes as an input a vector and maps it onto the real numbers, and we want to minimize that function. And the nice thing about the algorithm is that we do not need to know any knowledge about the gradient of that function, for example. So, and what we do is we set up a population of n sample solutions, so of n such vectors which we usually initialize randomly. And then once we have this population, we randomly take certain elements of this population, and we reproduce and we mutate them by combining and changing elements of that population more or less randomly. And after we've done that, we obtain a new set of vectors, and we select those vectors which are the fittest with respect to that fitness function and feed them back into the original population. And we repeat this process iteratively. And ideally, after repeating this process many times, the fitness of this population will increase. So this population will get closer and closer to the minimum, ideally the global minimum of this fitness function. However, the challenge, of course, is now to design a suitable fitness function. And in general, if we study modular stabilization via the F-term conditions, this would require knowledge of superpotentials, which is still a very difficult problem. However, we could look at a very specific background and a very well-known background, almost like a playground for flux compactification, is K3 times K3. Which has been studied quite a lot in the past. And the nice thing about this background is that, as has been highlighted in this paper here, that we can stabilize all moduli, actually all moduli, including scalar and complex structure moduli by fluxes. And there is no knowledge about period maps and complicated integrals of functions required whatsoever. So this is actually very well suited for this approach. What are we going to do? So we study G4 fluxes which have two legs on each of these K3s each. So by expanding in terms of the basis in terms of these middle cohomologies, we see that the four-form flux can be described as a matrix, a 22 by 22 dimensional integer matrix, because each of these cohomologies has dimensionality 22. So our population, our search space here will be integer matrices, 22 by 2 dimensional integer matrices. So we have to find a certain fitness function on the space of 22 by 22 dimensional matrices. And what is this fitness function meant to do? The fitness function should give a penalty if there's no vacuum at all. It also should give a penalty if not all moduli are stabilized. And as a bit more technical condition, it should also give a penalty if one of the K3 becomes singular. And then the last thing it should give a penalty for is this Q, this charge G4, which G4 is large, and in particular, if it is larger than chi over 24, which in this background actually takes the very nice value 24 itself. So whenever one of these conditions is violated, the fitness function will be large. And when all of these conditions are satisfied, the fitness function will be small. Therefore, searching for matrices with a very small fitness function actually will give rise to nice backgrounds with modular stabilization. So let me highlight very briefly a few details about the modular space of K3. So the middle core.
Just 1 minute. You've got a little bit less than 10 minutes if we want to keep some time for questions.
Oh, that's excellent. Thank you very much. So let me highlight a few details about the middle cohomology of K3, because that's the mathematical object we are most concerned. So the integer middle cohomology of K3 can be described in terms of this lattice, which is the even self-dual lattice of signature 3,19. I tried to depict that lattice here on the right, even though in reality it doesn't quite look like that. And then a point on the modular space of K3 corresponds to the choice of 3 self-dual 3 forms in the middle cohomology of, in this case, real-valued 3 forms, which give rise to so-called hyperkähler structure. And having such 3 forms, we can actually also make contact with the notion of maybe more familiar Calabi-Yau geometry. So we can take the first 2 of these 3 forms and combine them in that way, and we get a holomorphic 2 form. And we can associate the last of these 3 forms with the Kähler form. And as you know, having a holomorphic n form and the Kähler form on Calabi-Yau n-fold specifies a point in Calabi-Yau modular space. However, here we have this interesting or nice geometric notion, and we can think of these 3 2 forms spanning some form of plane within that actually. And an interesting observation is that whenever this plane in that lattice, this plane corresponding to the modular space, somehow aligns in a certain form with that lattice, such that a root of that lattice is actually orthogonal to that plane, then the K3 will have a orbifold singularity. And this is a situation we actually would like to avoid. So we can therefore use this kind of knowledge to stabilize modular stabilization on that background explicitly, and this has been done in this paper here. And so to do that, we expand the 4-form flux and also the intersection form in terms of a basis on the middle cohomology. So both in this case are 22 by 22 dimensional integer lattices. Matrices, and all we have to do is kind of to study these matrices and do simple matrix linear algebra manipulations. So then the first condition we want to give a penalty in our fitness function is to have not a Minkowski vacuum. And we actually do have a Minkowski vacuum if this combination of these matrices are diagonalizable and if all eigenvalues of these matrices are non-negative. And then the corresponding eigenspaces will give rise to these planes, and therefore will correspond to a point of modular space. However, procedure is only unique. There's only a unique such hyperplane if these eigenspaces have a definite signature eigenspace, and only then, therefore, all moduli are stabilized. So we give a penalty as soon as the eigenspaces do not have a definite signature. And the last thing we want to check for is whether there's a root orthogonal to that plane, which would then correspond to orbifold singularity. So whenever this situation occurs, we also give a penalty. And finally, we can very easily compute this charge, this Tadpole charge, as the trace of this combination of this matrix. And therefore, we also give a penalty if this charge is large. So now we are in a very good position to set up the search, because now we have a very well-defined mathematical problem, basically just a linear algebra problem on some integer, relatively large integer matrices. And we implemented that using the Julia programming languages, using some packages for differential evolution. However, there's a few challenges. The first challenge is that the search space is still incredibly huge. And another challenge is that the checks we do are actually very hard problems, namely checking for singularities, checking whether there's a root orthogonal to such a plane is actually an NP hard problem. So at every step in the search, we actually have to solve this very hard problem, and therefore still the searches converge relatively slow. And we try to adopt different strategies. We studied large populations, let them run over long times. We studied small populations, let them run over short times. And also we kind of did some form of brute force systematic search around the minima, which were found by this differential evolution algorithm. However, what we find is that we could generate more than, I think, 100,000 vacua, which have a charge Q equals to 25, but we did not find a single vacuum with a charge Q 24 smaller. And also as an additional check, we kind of translated this problem away from just this K3 times K3 application to a general lattice linear algebra problem and studied it for much smaller matrices. And we found a very similar behavior that we always found like minimal Q and then nothing beyond that. So, and here, therefore, in this situation, we conclude that the minimal Q is 25. So whenever we want to stabilize all moduli at a point which is non-singular, and push to the slowest 25. However, you should remember that on that background, this quantity on the right-hand side of the typo cancellation condition, chi over 24, is actually 24. Unfortunately, we see that we are not able to actually realize full moduli stabilization on that background with that I mentioned. We can go ahead and try to compute this constant, which appears in the Tadpole conjecture, by taking this minimal Q and dividing it by the number of moduli. And again, we find a value of roughly 0.44, which is, I think, very similar to some of the values which I quoted in an earlier slide. So maybe there is actually something going on around that numerical value. So let me conclude. So for M theory on K3 times K3, if we try to stabilize all moduli at a generic point in moduli space, meaning we don't have any modularity, and we want to have fluxes with arbitrarily small M2 charge with the Q smaller or equal than 24, turns out from our systematic computer search that we cannot have all three of them. So whenever we try to push the fluxes at a small charge Q, there will appear additional light degrees of freedoms, either from non-stabilized moduli or from gauge groups sitting at these orbifold singularities. We see this as evidence that Q flux somehow scales presumably linearly with the number of moduli. However, if we would take this statement in the most general way, our K3 times K3 example seems to almost generate a counterexample, because if we go to singular points in the modular space of K3 times K3, we can make this Q flux almost as small as we want, or as small as necessary. Therefore, one probably has to accompany that conjecture, at least in this example, with the requirement of the background being non-singular, or with the requirement of being at generic points in moduli space. However, K3 times K3 is still a rather special example, so it would be very interesting to see if the same behavior still persists for real Calabi-Yau fourfolds. And it would be also very interesting to get maybe a bit more direct, intuitive understanding of what's going on in terms of the Calabi-Yau geometry, which is currently a work in progress. So that's all I want to say at the moment. So thank you very much for your attention.
Thank you, Severin. Questions? Questions in the room or in the virtual room? No questions? All right. If there are no questions, we can have a break. Thank you again, Severin, for your nice talk.
Thank you.
20 minutes? Good. Miguel, can you hear me?
Yes, I can.
So it's Mario speaking. We can now, if you like, give you the right so that you can share your screen.
Good, I'm gonna do
And
that.
we will slowly start as soon as everybody is back in the room.
Yep, there we go.
Very good.
You guys
I
can see the
see.
screen, right?
So hold on, please. All right, I think, sorry, I think we can slowly start for the last part of the afternoon session. And our next speaker is Miguel Montero from Harvard again on the anomaly that was not meant to be.
Okay, well, thanks a lot for putting together the workshop, for the nice invitation. And I am just very sad that I cannot be there in person. Some people have sent me videos and it looks very nice. I'm sad I couldn't attend in person, but I'm happy. I'm excited to tell you about this recent work that I had in collaboration with Arun Debray, a mathematician now in Purdue, Marcus Dieriga, who is now at LMU Munich, and Jonathan Heckman at UPenn, about anomalies, the swampland, and some surprises. Okay, so the big picture question that motivated us, as usual, is to understand the space of consistent quantum field theories and quantum gravities. To understand the space of consistent quantum field theories, we have many different techniques, from typically conformal bootstrap, unitarity, causality, that sort of thing. And on quantum gravity, progress in this direction has been achieved via all the techniques that have been developed in the recent years in the swampland problem. Okay. So some of the techniques that are used in these two different approaches are very different, but some others are quite similar. In particular, there is one which is very powerful and works in both cases, and that is anomalies. Okay, so both in a quantum theory of gravity and in a quantum field theory, anomalies can provide consistency conditions that the theory must satisfy, particularly anomalies of a gauge symmetry, because they must cancel. So the question that we were interested in here, we wanted to answer a swampland question originally when we set out to do this project, which is, we wanted to understand why the duality group of type 2B string theory is SL2Z. Namely, suppose someone comes and tells you that they have a new alternate version of type 2B string theory, which looks like type 2B supergravity at low energies, but which is not SL2Z. So for instance, maybe it's a congruent subgroup of SL2Z. Well, we know this first possibility, SL2Z, is correct because it arises in type 2B string theory. So we expect that it's anomaly free. But maybe if we are lucky, we can explain why things like this cannot happen, because perhaps duality groups like this would have an anomaly. So that's the question we set out to answer. And you can ask, well, why are you trying to answer this question now and not 20 years ago? We knew about anomalies 20 years ago, and that is true. But there has been recent mathematical developments, and also coming from the field of condensed matter physics, that allow us, it only happened in the past few years, to compute anomalies efficiently in a way that we were not able before, using a mathematical framework known as covordism theory, which will be part of the story I'll be telling about. Okay, so the plan of the talk is the same as the structure that the plan that we had originally for the project. So when we set out to do this project, we said, okay, we're first gonna learn what are the new developments in anomalies, and then we're gonna apply them to the duality group of type 2B string theory in 10 dimensions. And once we check that that one is anomaly free, we can apply it to other duality groups. Okay, and then we can say which possibilities are in the swampland and which possibilities are potentially in the landscape. So that gives us constraints. That was the original idea, but things don't always happen as you like them to. And it turns out that when computing the anomaly of just plain vanilla type 2B, we found a big surprise. which obstructed further progress in this work. So actually, this talk is going to be about that surprise. And the surprise is none other than it turns out that actually the duality group of type 2B string theory, in fact, has an anomaly. Okay. So nevertheless, I can still proceed with the first part of the outline, and I can try and tell you first a review of what is an anomaly. Well, an anomaly is a classical property of a theory. It's a property of the classical theory which is not preserved under quantum effects. And typically, the things that we're interested in are symmetry. So typically, an anomaly is used to refer to a symmetry of the classical theory which is not preserved under the inclusion of quantum effects. One way to encode this lack of symmetry once you introduce gauge fields is it manifests itself as the lack of invariance of the partition function when you couple to background gauge fields. So when you have a symmetry, you can couple the partition function to a gauge field, and it can sometimes happen that this partition function is not gauge invariant, and that's what the anomaly is. Okay. So the way I put it here is this lack of gauge invariance is in principle is not an inconsistency of the theory as long as this gauge field is background. But when you make the gauge field dynamical, it turns into an actual inconsistency of the theory. Okay, so what are the possible classes of anomalies? Well, broadly speaking, there's two classes. You can have local anomalies or global anomalies. A local anomaly is an anomaly in a gauge transformation which can be continuously deformed to the identity, to do no gauge transformation. And a global gauge anomaly is an anomaly in a transformation which cannot be deformed to the identity like this. For instance, if you have a discrete symmetry group that you're talking about, as will be the case for us, because we'll be interested in the duality group of type 2B string theory, then a global anomaly, then all the anomalies are global, because these discrete groups, if you do a gauge transformation, you cannot continue to deform to the identity. So how do we understand anomalies? Well, local anomalies are an old story. I expect most people here are roughly familiar with the idea. It has been understood since the 80s. And the point is that one can understand what the anomalous variation of the path integral under our local gauge transformation is very efficiently in terms of a construction given by some polynomial. If you have a d-dimensional theory, you're interested in computing anomalies in a local symmetry for it, you can construct by a well-defined procedure a d+2 dimensional anomaly polynomial. And that anomaly polynomial encodes the anomalous variation of the action. And basically, absence of local anomalies is the same statement that this anomaly polynomial, when sum over all the fields in your theory, actually has to vanish. So that's the requirement that local anomalies cancel. And actually, this is the case we will focus for the rest of the talk. As I said, we're interested in type 2B string theory and in type 2B supergravity. This actually happens. This is a famous anomalous cancellation you can read about in Green-Schwarz-Witten's book. That there's 3 chiral fields in 10-dimensional supergravity, and they're anomaly polynomials. They all have very different coefficients, but they all conspire to produce a miraculous cancellation and have the theory being anomaly-free. Okay. So this is what we do for local anomalies. What should we do for global anomalies? Well, understanding the understanding of global anomalies or how to compute them up until not so long ago was quite artisanal. So you would often take you could often find you could consider that you would look at a particular gauge transformation and which you want to understand if it's anomalous, and you would maybe enlarge the gauge group, and in that way it becomes a local anomaly, and so on and so forth. But since not so long ago, there's a very systematic way of understanding these things in terms of an auxiliary topological theory in d+1 dimensions. So if you have a d-dimensional theory, and which can potentially have gauge anomalies, what you do is you construct. There's a recipe which I won't tell you because details are not needed here. But there's a recipe to construct an anomaly theory, which is a theory in d+1 dimensions, and it's topological. Topological means so that this is basically this anomaly theory. You can compute this partition function on a manifold, and you can also turn in a background gauge field for whatever symmetries you were discussing. And the statement that the theory is topological means that the value of this number, the value of the partition function on this manifold with this gauge field, doesn't change when I deform the metric a little bit or when I deform the gauge field a little bit. Okay, so that's what it means the theory is topological. But actually, for the anomaly theories of the theory that we'll be interested in, a much stronger property is true. It's not the anomaly theory is not just invariant under small deformations. It's actually invariant under a much more general, much more coarse transformation, which is called a cobordism. So what is a cobordism? Cobordism is if you have, suppose that you have a manifold, T plus one dimensional manifold M with connection A, and a second, possibly topologically different manifold, M, this would be M prime, with connection M prime. It can sometimes happen that these two manifolds together can be written as the boundary of a D plus two dimensional manifold, B D plus two, such that the values of the connection and gauge fields here and here, they extend to a connection also over D plus two, so a non-singular connection over D plus two. When this happens, you say that M A and M prime, A prime are cobordant. And the statement that the anomaly theory is invariant under cobordisms is the statement that it takes the same value, partition function takes the same value here and here if the two manifolds are related like this. Now, this relation is extremely powerful. It is very powerful because you can actually consider the set of all manifolds with connections and quotient by this boundary relation, which is actually an equivalence relation. And the resulting thing that you get is, it's actually a group, has an abelian group structure. And it's in all the examples that I've ever found in physics, it's a finally generated abelian group, which it's called the Bordesian group with symmetry structure given by G. Okay. Now, this is great news because this only has, if it only has a finite number of generators, to be sure that your theory is free of global anomalies, you just need to evaluate the anomaly, this anomaly theory, on a finite number of manifolds, the generator of these things. And that's all you need to do. So there's a very simple three-point strategy for computing anomalies that follows from this perspective. Number one, you first determine the symmetry type of the theory, and meaning what are the symmetries that you're interested in, and the cobordism group that controls the anomaly. This is easier said than done. In fact, a large part of our work was to compute this cobordism group, and it was only possible thanks to the impressive knowledge that Arun has of spectral sequences, which is the technique that mathematicians use to compute these kind of things. Once you have the Bordesian group, you still need to find, and there's a little bit of physics involved here, you still need to find the right anomaly theory. You need to construct it. You need to say which topological theory you're evaluating in the Bordesian group, in the classes of the Bordesian group. And finally, you need to just do this. You need to evaluate the anomaly theory and the generators of the Bordesian group. And if the answer is 0, 0, 0, 0, 0, then there's no anomaly. Okay. This is very general strategy. So maybe it's also like good take-home message if you want to compute, if you want to get in the business of computing anomalies like this. But for the rest of the talk, I'm going to be doing this for the duality symmetry of type 2B string theory. Okay. Before I do that, I need to tell you exactly what is the duality symmetry of type 2B string theory. And you know, the usual answer that you can find in Polchinski's textbook, for instance, is that, well, type 2B supergravity has right on the nose an SL2R continuous symmetry. But this is actually broken by quantum effects, by drag quantization, by the spectrum of charged branes to an SL2C. So you would say the duality symmetry of type 2B string theory is SL2C. But this is not quite right. This is to see, and to see why it's not quite right, the best thing to do is to use M to F theory duality. So F theory represents this SL2C as the diffeomorphism group of the torus. And when you go back to M theory, you compactify on T2 and go back to M theory, this SL2C actually becomes the physical diffeomorphism group of a torus, of the M theory torus. So it's actually part of just M theory's diffeomorphism symmetry. But from this point of view, it's pretty clear that the duality group cannot be just SL2C. Why? Well, M theory has fermions, and fermions you know, when you rotate a fermion, when you rotate a fermion by 2 pi, it picks a minus sign. You can, for instance, rotate by 2 pi by acting with four quarter rotations, which are elements of SL2C. And in SL2C, that the fourth power of the S generator is actually 1, but actually because of the fermions should actually be 8. So it should be -1, sorry. And that means that once you take fermions into account, the duality group of M theory is actually not SL2C, but a double cover of SL2C, which is called the metaplectic group. Interestingly, this is not a matrix group. It has no matrix representations, unlike SL2C. But this is not the only thing that happens, because M theory also includes reflections. M theory makes sense on non-orientable manifolds of a certain type. And so you can do diffeomorphisms where you just flip one of the coordinates of the torus. And that actually enlarges SL2C further to actually yield general linear transformations with coefficients on the integers. Now, whenever you see a diagram like this, you know there has to be something on the other corner. And it turns out that indeed, the actual duality group of type 2B string theory, which takes into account the fact that it has fermions and also includes reflections, is something which we call PIM plus or GL plus 2Z, which is the PIM plus cover of the group GL2C. Okay, that's what it is. Some abstract group with slightly different generators than the one you're used to. But okay, we already have this group. We identified the symmetry group of the theory, and now we need to compute these Bordism groups. And the first step is identify symmetry group, compute the Bordism group. I'm condensing many pages of calculations into the following result. But this is what it is. So we're interested in an 11-dimensional Bordism group, because remember, the anomaly theory has d+1 dimensions for a d-dimensional theory, and we're interested in anomalies of type to be in 10 dimensions. So this is what the Bordism group is. And we could have been lucky. It could have turned out that this group was 0, and therefore we have nothing to compute, and then type 2B would have been trivially anomaly free. When you look at it like this, it seems it's clear that it has several potential anomalies. But that's not that's just step 1. Step 2, we need to determine what is the precise anomaly of type 2B string theory. Now we have very, very good techniques to compute things, to compute what the anomaly theory is for chiral field theories. The fact that the type 2B supergravity involves the self-dual form, of course, complicates things. But this problem has actually been solved. There's been a lot of progress on this problem in the last decade by the work of Montero, and we followed an approach by a recent paper by Shie, Tachikawa, and Yonekura, where they just write down exactly what the anomaly theory of this is, including the self-dual field. Okay, so this is the anomaly theory. It depends on it has 3 pieces, so you get contributions from the usual chiral fields of type 2B supergravity. So there's one piece coming from the gravitino. These things here are called, these are the eta invariants of the Dirac operator associated to the gravitino. It's a particular regularized sum of eigenvalues, the details of which are not important. The important thing is that we know how to compute this. There's a contribution coming from the dilatino. There's a slightly more complicated contribution coming from the self-dual form. And finally, there's a term which is actually related to the form, but which we can understand as coming from the Chern-Simons term of type 2B supergravity. Type 2B supergravity has a C4 wedge H3 wedge F3 term. And that means that H3 wedge F3 couples as a background field for the self-dual form, and therefore plays a role in the anomaly theory. So this term is just some function which is called a quadratic refinement of this z hat thing that I wrote here, and this z hat thing that I wrote, for all intents and purposes, is basically H3 which F3. Okay, so the value of the anomaly theory takes into account what are the fluxes that you turn. They also matter. Okay, whether or not they contribute to tadpoles. I'm assuming that there's no tadpole here, so the total contribution to tadpole in the end vanishes. So this is the anomaly theory. We have the Bordism group, so we can just go ahead and evaluate everything. We have here all the factors in the Bordism groups. We have generators for each factor, and finding the generators for each factor was actually not easy. They involve length spaces, the quaternary projective plane, and some more exotic manifolds that they actually were not discussing the literature as far as I can tell before our work. But what matters for us is that once you evaluate the anomaly theory in these classes, there's a bunch of them which are 0. There is 2 classes in which we cannot evaluate the anomaly. This is a technical abstraction that we have, and I can talk more about it. But here we know that it could be vanishing or perhaps 1/2, meaning, so the value of the anomaly theory is a map from borders and groups to U1. So you should understand this as integer, as numbers modulo the integers. But what matters is that for these classes, we can certainly say that the anomaly does not vanish. So I think I perhaps a little bit early, this is a very big surprise. Type 2B string theory is anomalous and therefore inconsistent. By MF duality, that means that M theory has a differential invariance. And that means, of course, that string and M theory are not consistent quantum theories of gravity. So we should all just go home. Okay, I see there were no questions. So you guys didn't believe they were actually the conclusions. And that's good, because they are not. It's good that string theory has solved more complicated problems than this. And here also there's a miraculous string theory solution to this problem. So of course things are consistent in it. And the solution is the solution, at least the solution that we found, is that there's a simple modification of the type 2B Chern-Simons term. So you just take the original Chern-Simons term and you add some piece I new. This piece I new has a weird expression. But what matters is that it's a purely torsion characteristic class that depends on the characteristic classes of the duality bundle. In the same way that you characterize a U1 bundle by a cohomology class, the Chern class, you can characterize discrete bundles like SL2C bundles in terms of other characteristic classes whose details have not discussed, because they also don't matter for the gist of it. But there's a new class, a new contribution you can add to the duality bundle, and this new characteristic class, because you're adding it to the C form term in the action, basically shifts the anomaly theory from what we had before to a piece, which is what we had before plus this new piece. This piece is switched off whenever we don't have a duality bundle. Whenever we don't have fluxes. But this new piece can be turned on if we just have geometry and a duality bundle. So once you take this piece into account and its form is fixed, it turns out that you can make all these new anomalies vanish. Okay, so they all cancel. Basically, we are modifying the type 2B action with a new discrete coupling that had not been noticed before, because you cannot see it in string perturbation theory or in supergravity. That works in such a way that all these anomalies cancel. They all cancel. These ones, we don't know if they cancel or not, but as I said, they potentially cancel. And a beautiful thing is that I drew a line here. There's a qualitative difference between anomalies above the line and below the line, and only the anomalies above the line can be canceled by our new mechanism. So this is like a small consistency check. If we had had that this class, for instance, was anomalous, then we wouldn't have been able to cancel it with this mechanism. But precisely those anomalies that can be canceled with the mechanism are the ones that were non-zero before. Now, the way I told you this is like, okay, fine, there's some new anomaly, and you cancel it with some top coupling. That's good, okay? But I want to emphasize that this only works because of some precise cancellations that totally depend on the detailed type 2B spectrum. So to exemplify this, I will focus on the first coordination class in the table above, which is that of the Z27 anomaly. Now, the fact that there's a modulo 27 anomaly, that the Z27 factor in the coordination group, means that the corresponding anomaly can take any value modulo 27, can take any integer value modulo 27. And in fact, it's very easy to write down 10-dimensional spectra, where you just change the representation, the SL2, the duality group representation of the gravitino or the dilatino, in which the corresponding anomaly is just any integer modulo 27, just any integer that you want. Okay. Now, the mechanism that that we explained won't work for any K. In particular, if we demand that anomalies also cancel without a duality bundle, this mechanism would only work for K equals 9, which is precisely the value that is produced by string theory. Okay, so it really, string theory had a 1 in 27 chance of getting it right for this Brodisson group, and then there are others. There's a 1 in 8 chance of getting it right in the Z8 factor, and there's a couple more Z2 factors. So it really depends on the details of the type 2B spectrum that this works. Okay, so so what we propose is nice, but how can we check it? Well, this is unlike what I've been telling you so far, which was quite rigorous. This involves some steps which are not completely clear, some heuristic steps. But it seems that our theory also matches the duality anomaly of n equals 4 Superior Mills. So what do I mean? N equals 4 Superior Mills is holographically dual to ADS 5 × S5. And a very general feature of the ADS-CFT correspondence is that an anomaly in a global symmetry in the field theory side becomes a topological term in the, it's encoded into a topological term in the bulk action. Now, it was studied recently, again by Tachikawa, Shea, and Yonekura, that n equals 4 Superior Mills has a Montonen-Olive duality anomaly. So the SL2Z duality of n equals 4 Superior Mills has an anomaly, and the bulk term that would predict this, that would match this anomaly was not there in the literature, and our term, with some caveats, seems to capture precisely the contribution from the Montonen-Olive duality anomaly. So it's a small cross check that you can have of this term. So in the end, this is a happy ending for type 2B. So type 2B here is very happy, but like any good story, this story has a twist ending. Because even though I just described a very nice, simple mechanism by which anomalies can cancel for the duality symmetry of type 2B, we also found alternative ways to cancel the anomaly, following an approach outlined in this paper of the topological Green-Schwarz mechanism. In this new approach, you introduce new additional discrete fields to the spectrum of type 2B string theory. They are discrete fields, so they don't change the supergravity description. Supergravity is always the same. But by tuning the couplings in a certain way, you can introduce you can make it so that the topological action of the discrete fields you introduce, kind of like it's kind of a BF action, has the same anomaly as the spectrum of massless fermions of type 2B, so you can cancel one against the other. Now, these theories are definitely not type 2B, because the equations of motion for these discrete fields force additional tadpole conditions that exclude backgrounds that we know are there in type 2B. For instance, type 2B makes sense on Z2 mod gamma. This is one of the best studied backgrounds of type 2B. In this theory, it doesn't. In this theory, that background breaks one of the tadpole conditions that you would get from this. So these other alternative theories are definitely not type 2B string theory, but they only differ in the non-perturbative spectrum. They only differ in the spectrum of non-perturbative branes. The low energy dynamics is exactly that of type 2B. It's exactly the same. You wouldn't be able to tell them apart the low energies. So of course, the obvious question that we want to ask is whether these theories are consistent, or perhaps they are in the swampland. We just don't know. And more generally, this is part of a more general question to which I don't think we have a good answer, which is, can there be more than one consistent quantum gravity with the same low energy limit, even for supersymmetric theories? For instance, in M theory in 11 dimensions, people have proposed a discrete theta angle that supergravity admits. And we just don't know if that means there's two versions of M theory. So there are similar considerations for type 1 theories. So perhaps the M theory star should be replaced by an M theory flower like this, where you have several points which project to the same thing at low energies. And with this, I'm basically finished. So just to wrap up, there's an anomaly in type 2B, but it was not meant to be. You can actually cancel it due to detailed properties of the type 2B supergravity spectrum by a subtle modification by discrete terms of the Chern-Simons coupling. And of course, we would like to understand what are the implications of these couplings on the duality wave. And of course, we would also like to be able to evaluate the anomaly in the one class that we could not compute, the mysterious manifold that we called XLF. So with this, I thank you for your attention, and I finish.
Thank you, Miguel. Thank you. There is a question in the audience in the room here by Dieter.
Mhm.
Hi, Miguel, can you hear me?
But very, yeah, I cannot hear very well, Dieter, but yeah.
I try to speak clear and loud. So, first of all, indeed, I was about to complain when you had your intermediate conclusion, but never mind. And secondly, this is a little bit reminiscent. It's a kind of déjà vu for me about some work which was done roughly 30 years ago, namely about indeed duality anomaly cancellation. At that time, it was about T-dualities. So in the lower energy effective action, actually, with Luest we have a paper which starts in the title Duality Anomaly Cancellation. And indeed, it happened there that for several backgrounds, the T-duality anomalies were anomalous. And these anomalies could be cancelled also by some extra terms in the action, which involve the dilaton field, the S field, because the S field transforms non-trivially under T-duality. So the conclusion was very similar to yours. These theories are fine and they are okay, they are good backgrounds. So my first question is whether you can remark on this. And my second question is, if you would now go down dimension and go to some string dual description, the S duality you're discussing could become a T-duality in some other corner of the duality web. So would perhaps suspect that there's a direct connection also to these T-duality anomalies in lower dimensional string theories.
Yes. So to your first question, correct me if I'm wrong, but I believe you're referring to the work by Gabriel on this. This was late 90s, I think, on the duality anomaly of type 2B. So in that work,
I think the work started in the early 90s by work also by Kunas, Derendinger, and then also with Luest I worked a lot on this. So it was before Gabriel's work.
Yeah. So about the other work, I'm not familiar. And if you could send me some reference, I'd really appreciate it. The work by Gabriel, which indeed is closely related to ours. They also study anomalies of type 2B with duality backgrounds. But the duality backgrounds, and they end up concluding that you need to add some topological terms to the action, which are different than the ones that we include. The anomalies that they discuss, they are actually not pure type 2B supergravity anomalies. They only appear in backgrounds with D7 branes. So the terms that they consider, they are only ever non-zero if you consider a background where the axial dilaton has non-trivial has a singular profile. For instance, if undergoes a monodromy like tau goes to tau plus 1, like T-duality as you were saying, then that's where a term like the ones that they have can be it's turned on, and then you can actually match it with other terms that you can get from the duality web. But these are terms, for instance, that you see in ordinary cohomology. The terms that we have here are pure torsion, and the anomalies that we study appear even if there are no D7 branes. The anomalies that we have, that we study, appear even for completely smooth supergravity backgrounds. So that's perhaps a difference between the two of them. And the second question, if I understood correctly, you're asking how do I follow through this? How I follow through these terms that we want to put through the duality web, right? And that's a very good question. And I can only say vague things such as that. Of course, when you go to M theory, it should be part of the diffeomorphism anomaly of M theory. But it's notoriously difficult to follow these discrete terms throughout the duality web. For instance, M theory has this condition that if you compactify on a manifold which has non-zero force Stiefel-Whitney class, the G4 fluxes have interior quantized. It's not so easy to see what that maps to. For instance, when you go to F theory, is a subtle condition on the allowed values of some curvature invariant in innate manifold. So it's often difficult to translate from one to the other.
Okay, thank you. Actually, these anomalies with respect to T-duality, these were also emerging in pure supergravity theories. So no brains. So this was a heterotic setup. So no brains, only pure supergravity.
So Dieter, if you could send me papers for this, I'd be very grateful.
I have prepared the email already. It will go out now.
Okay. Yeah.
Thank you. Are there other questions here? No question. Yes, there is a question. Yes, please. Yes, Manu.
Hello.
I think the microphone is not on.
Very loud now. I was just wondering whether you could say a little bit more what X11 was, where you couldn't compute the.
Yes, very good. So X11 is actually is not that weird. It's a quotient of a product of spheres S5 times S6 modulo as Z2 times Z2 action. The thing that makes it the thing that makes it complicated, the computation in X11. Okay, maybe I can share screen again a bit. So the thing that makes computations of X11 complicated is that we need the anomaly. It's basically we don't know how to compute. So this is the anomaly theory of type 2b. We know how to compute this term, and also the first part of this term in X11. But we don't know how to compute this Q or this term, the alpha invariant, which is related to Q. The problem is that to compute this anomaly theory, you need to choose a particular. This Q here is a refinement of the intersection pairing it's a quadratic refinement of the intersection pairing in the 11 manifold, and there's more than one choice. In general, there is more than one choice. In the other generators of the Bordesian group, the manifolds that we find, like this lens space or this quadratic space, they admit a duality. You can turn on and off the duality bundle as you wish. So by studying anomaly cancellation, when there's no duality bundle turned on, we can determine the value of Q, and then we can compute the anomaly when the duality bundle is turned on. And that happens for every class here except for X11. And the reason for this is that X11 does, unlike the other manifolds, which are pure spin manifolds, in which you can define spinors even though there's not a duality bundle turned on, X11 is not spin. Okay. So you need to always have a duality bundle turned on to compute the anomaly. So sorry for the background to make sense, and that means that this trick that we use to determine the Q doesn't work in this particular manifold. More generally, there should be a prescription. There should be like a full top-down prescription to compute what is the correct Q for each manifold that you study. It's a choice of a canonical choice of quadratic refinement. And in mathematical terms, this is done for spin manifolds for all these guys. So you can just do it for all those guys. But because X11 is not spin, there's no known canonical choice of quadratic refinement. So all that we can say is that this part of the anomaly vanishes, and then we can constrain what are the possible values that the other part of the anomaly can take. And indeed, it can take either 0 or 1/2. So that's all we can say. But my point is that there's a physics question that we need to settle if we want to compute anomaly in X11. We need to know what is the recipe to compute a canonical quadratic refinement for a general manifold with a spin yield plus structure as opposed with just a spin structure. I don't know if that was clear or.
All right. It was fine. Thank you, Miguel. If there are no more questions, let's thank Miguel again and move to the next last speaker of today. So, yes, next speaker is Pouria Mazloumi, and I think the slides are okay. All right, extracting by gravity. Sorry. Pouria is from Munich. And now finally the title, Extracting by Gravity from String Theory.
On the laser. Okay, thank you so much for this opportunity. I know it was a schedule changing, and it's a great honor to be here, at least finally in person and doing the conference and giving this talk. So this is an ongoing paper project on somehow extracting by gravity from string theory. This is the first paper. Hopefully, it's going to be soon a second paper. We did this project. This project was suggested and organized by Crisula Marcu, the postdoc at MPP, and led, and we did it in collaboration with Professor Luest and Dr. Stiebegger, myself. Okay, so I'm trying to keep it concise, and because we have things to do during the night. What I hope you would know at the end of this talk would be that what is biometric gravity. It's a bit of a new thing, but hopefully most of you know about it. And then I'm going to do a small review on perturbative string amplitudes to at least create a context of what I'm going to talk about. And then the setup that we're going to create in a string theory and field theory, because biometric gravity is a field theory description. And then try to compare results and see what's going on, can be constructed. So from the title, you would know we're going to try to somehow reconstruct the biometric gravity to a string theory. Okay, so let's start very, very simple. We think we know gravity, at least at the classical level. We required some Lorentz invariance diffeomorphism and some other physical well-behavedness and structures. And that led uniquely to the Einstein-Hilbert action, which is all we all know, and that's the point of departure that we're going to discuss. So the first attempt to somehow quantize gravity came from this linearized gravity, where you have a classical solution, you perturb around the classical solution, and then you hope good things happen. For the structure, okay, the simplest one was that around Minkowski, you have the Minkowski, and then you have the perturbation around the Minkowski, and after linearization, we end up with this famous operator that we have for this quadratic structure. So that's exactly the procedure that I'm going to follow also we're going to follow for the biometric gravity. I'm just trying to create a parallel of what exactly is going on. So for the symmetries, we have the diffeomorphism, the famous symmetries of GR. And for the linearized version, we have the linearized diffeomorphisms, which can be used as any other symmetries in physics to organize degrees of freedom in such a way that is better to handle, like the gauge theories. And when you do that, there's very different gauges that people use. For our purposes that we're going to see, it's better to use the TT gauge, the transverse traceless gauge, which is really look like a gauge theory structural gauge symmetries. Okay, so let's move on to the biometric gravity. I'm going to motivate a bit biometric gravity here, and then I'm not a super expert in biometric, but I'm going to motivate it, and I'm just going to structurally try to at least go through the alphabet of biometric gravity. So one of the main motivation would be that we have a standard model of particle physics that we know we have a spin 0, a spin 1/2, a spin 1, and then the question would be what would happen if we add other content like a spin 2 and higher spin. So the problem would be that, okay, for higher spins, there is a huge kind of worm that there is theorems, and then you end up with all of the spins and many other issues. What one can do is try to see if we can now couple and only a spin 2. And for that, we can use it maybe, okay, there are different suggestions, but maybe we can use it as a candidate for dark matter. And the analysis that's been done here by Bochev and Agnes Schmidt et al., Schmidt-Mayan et al., gave some sort of a bound if that spin 2 is going to be a dark matter candidate on the mass of it. So what is then biometric gravity? So biometric gravity, as I said, we have the by gravity, we have two metrics. So we have two Einstein-Hilbert actions, like for the metric G and metric F, and we have respective Planck masses for each of them. And there is a potential that basically connects these two. The problem before, this is the paper by Hassan Rosa in 2011, the problem was that coupling an spin 2 to gravity had issues, like there were discontinuities and ghosts, and the same problems that when people try to construct massive gravity. And this structure is uniquely fixes it in such a way that it's not ghost fixed. So this is symmetric polynomials, and this is the structure of the symmetric polynomials in terms of the metrics. So this is, you can see this S defined in terms of G and F, and the S's are now multiplied together, contracted E's, and then these are going to be from 0 to 4 going to give us the biometric potential. So now what are the symmetries? So if you look at this action again, naively, if you forget about this part, now we have a diffeomorphism for F, we have a diffeomorphism for G, 2 copies of diffeomorphisms, and we see there is happening a mixing through this potential. And so what we're going to see later is that, okay, we seem to have 2 sets of diffeomorphisms. If you remember talk yesterday, seemingly there are 2 diffeomorphisms, but we're going to see that they're going to entangle through the biometric potential, and at the end of the day, we're going to have only 1 diffeomorphism. So if you look at the equation of motion, we have the equations of motion for the G and the equation of motion for F, and this parameter, this is basically the ratio of the Planck masses of F and G. So the matter content, so there is a choice to be had here about what is going to be the universe that we are talking about. So what the matter is defined with respect to, and here the matter is defined with respect to the G, and that's the reason that T is appearing inside the equation of the Einstein equation for the G, not for the F. Okay, so using the so now I'm going to follow up again on the same path that we had before for the linearized gravity. What's happening is that we need again a background, and we need a background to classical solution, and then do the perturbation. There are all solutions of Einstein gravity exist in biometric. You can construct all of them. We choose the simplest one, the proportional background one, which means that G and F are connected through a coupled positive constant. And again, simpler, you can just fix both of them to Minkowski. And doing that, doing basic linearization, we end up with some terms that are omitted writing it because they're going to be huge terms like the one that we saw before, and they're not going to be useful for our purposes. For our purposes, we need to rotate these and go to mass eigenstate. And if you rotate these, and you can see there's just a rotation, going to the mass eigenstate, we're going to end up with a massless, and I'm going to say why it's going to end up with a massless, and a massive field. Meaning that if you calculate the equation of motion for basically G and F, plugging back for this structural rotation of the definition, we end up with things that look like a massless, basically a massless equation and a massive equation with like a Fritz Pauli mass. So we have a massless gravity and a massive gravity. And now we can again look back at the symmetries and see, okay, we started with 2 sets of symmetries. Through this mixing, we somehow entangle the 2 of them, and the diagonal part of these 2 diffeos is going to be the 1 diffeo that survives and going to go through this massless part of it. So the massless graviton, massless spin 2 is going to be graviton, going to correspond to the diffeomorphism of that universe that has the massive field 2. Okay, so this is the setup that we're going to have for the biometric. So what are we going to do? We're going to go look at the different interactions inside the biometric. We're going to find out which interaction we're going to use, and then we're going to do some sort of gauge fixing to get rid of, okay, because of the string, I'm going to discuss that the string structures are basically gauge fixed in the sense of field theory, and then we're going to compare these amplitudes from the string side and Lagrangian terms in the biometric side. So one more important thing is that there is a important amplitude that we're going to discuss also later in the next paper, the G squared M. We're going to look at 2 amplitude, the cubic, the self-cubic M cube, and GM squared, meaning the decay of the graviton into the 2 massive. But the G squared M is other amplitude than one can look at, but the point is that the biometric gravity does not have this as a identical feature, and that's what would be something that one can look at to see if it's going to be a good theory or not. But okay, the 2 amplitudes that we're going to look at is going to be GM squared and the self-cubic interaction. So looking back at the literature, this has been done before. This is the M cube interaction from the biometric gravity, and this M cube interaction looks like, okay, this is a huge term that we need to take care of. And the same thing happens for the GM squared. There is also the huge terms that basically, as you can see, there are always 1 graviton and 2 massive spin 2s, massive gravitons. Okay, what the notation of calling it can be different. Now, can we use all of this? No, because we're going to go and compare unshell amplitudes of a string theory, and because of that, we need to impose the unshell condition of string theory somehow onto this. And we're going to go back to the discussion that we had before, and was that we have a massless spin 2. Again, you can use the linear diffeomorphism for it and keep the TT gauge. We have a massive spin 2. The equations of motion of it, which was basically the Fritz Pauli mass, gives a condition. We can show that condition that's going to be a TT field, a transverse traceless, basically as I showed the condition before. Imposing those conditions into these two Lagrangians here that we had, we give us these two terms. So the many terms going to go away, and we're going to only end up with these four terms here and these terms here. As you can see, the information about biometric theory is now very limited, because as if you remember, in the basically the identification of the biometric gravity was through these betas that was corresponding to the biometric potential, and so the only information left is living here. Other things are more or less the generic Lorentz invariance possible terms that you can get. But okay, that's the structure that we have after the gauge fixing. So now we're going to depart from field theory. So everything that I told you just now, it was field theory. Now I'm going to depart from field theory, just do a small review of the perturbative string theory and then do the comparison. So in the, okay, as I'm sure most of all of you know, what we do when we compute the amplitude, basically insert the vertex operators, find the correct Riemann surface, and then just do the integration. Now, in this case, we have a closed, okay, I'm going to discuss which state we're going to have, but the point is I have the disk already here, so it means we're going to have a at least open string and, okay, also closed string. And the measure, as you know, okay, depending on what is going to be real and closed, is going to be dz and dx, and, okay, the Green's function that is associated to it. So what is the state? So if I'm going to compare this biometric gravity to something inside the string theory, I have to choose a candidate of that state inside the string theory. So for the graviton, we have a candidate. We have the type 2 string theory, and we know, okay, I can take the closed string, okay, in the SUSY or non-SUSY case, and that would be at least the first candidate for a massless graviton. So that's a state, at least there is a history for it. But then what's going to be the massive part? For the massive part, we took, okay, there is a paper, okay, I have written it also here. There was a paper by Dieter and Ferreira and Kahagias that they discussed that if you look at Weil squared gravity, and inside that, the construction of the biometric theory with a massive graviton was there. So, and that associated to an open string massive state. So that's the reason that in this project, I'm going to go back and show the vertex operator. We're going to choose in this case for the open string in this this specific state. So if you can, okay, the diagram also, we want something that is symmetric, spin 2, and for the symmetric spin 2, for the massless, okay, we know we can take the closed string, but for the massive open, we take the open string, and inside the table of the open string created by generators acting on the vacuum, we're going to end up with this specific state that comes from here. So we take this, and the vertex operator is, okay, one should go through the BRST and fixing the symmetries and stuff. And if you do that all, which is a straightforward calculation, and it has been in many papers, we end up with this vertex operator that's associated with the spin 2. Okay, so just a recap, we need 2 degrees of freedom for our graviton, or 35 in 10 dimension. The 2 is in 4 dimension. Doing that, this has been done many, many times. This is one of the many, many references that has been done before. One can end up with gravity amplitudes, basically the 3-point amplitude of the graviton. And this is the vertex operator, the famous closed string vertex operator. For the massive graviton, massive spin 2, we need 5 degrees of freedom in 4 dimensions, or 44 degrees of freedom in 10 dimension, depending on which dimension we're looking at. And for that, because of the structural behavior that has been seen already in the Weil squared gravity, we are choosing the open string, and and we are choosing the open string, and the state of it, the vertex operator, is given by this. So we know the open string and the closed string, and hence back the d squared in the correlator that I just showed you. So we're going to take this state and compute the amplitude. Okay, it's also a graphical picture of what's happening. So we have the amplitude that looks like this. We have the closed string coming and going to interact with the two open strings that we have, which is going to be 2 massive, and schematically we're going to go on the disk, and the disk mapping in upper half plane. So the integration domain is going to be basically the real line, and the H plus the upper half plane. Okay, so doing that doing this contraction requires some modification and on-shell conditions, and on-shell conditions, as you can see, basically for a string theory corresponds to the TT gauge, and hence again going back to why we fixed the TT gauge, because the state of the string theory that we wanted to compare with already satisfied this condition. So we had to somehow enter this information back into the field theory side. So we have the TT structure, and you can see the mass of the massive state is going to first excited state. So we have the -1 here, and the symmetry, the momentum conservation of momentum, and the Mandelstam variables is given in this structure. As you can see, we have the conservation of momentum parallel to the brane, and there's a D matrix that corresponds to the direction of the Neumann and Dirichlet boundary condition in space-time for the different momentum. Okay, so we can define the ST and U channel, and we have only one. Okay, if you do the conservation of momentum, you know we have only one independent Mandelstam, which one you want to choose, and do the calculation. So the calculation itself, the contraction is one level of hardness. There's a huge contraction of partial X's, fermions, and everything contracting with each other. We order them in the paper in the order of x1 minus x2. So x1 minus x2 are the positions of the open strings that are going to be real. So x1 open string 1, x2 open string 2. And so the position, the contraction gives us x1 minus x2 in different powers, and we fix them. We order terms in terms of x1 minus x2 i's. So as I said, the first problem is that you have many contractions. That's not much of a problem. You have to do the calculation. The second problem is that we have to do the integration, because now you have the SL2C. Okay, in this case we have SL2R because it's a this, but we have a closed string, so there's at least one real variable left. So one has to do the integration. Doing the integration give us some gamma functions, and the gamma function needs to be expanded if you want to go to some sort of field theory limit. So alpha prime should goes to 0. So we have to take this alpha prime to 0 limit to at least look at what's going to be the field theory corresponding result. And doing that needs some sort of careful analysis, because if you look at this, so we have this result for the amplitude. So this is for A4. So when x1 minus x2 is to the power, there's a huge term. You can look at it in the paper. As you can see, S, depending on which one you're choosing, ST or U, as I said, there is only one independent Mandelstam variable. Here it lives inside the gamma function. So we have to somehow do the expansion. But when we are looking at it, it's going to be tricky in the sense that when we take alpha prime goes to 0, if you are, okay, K1 and K2 being the open string momenta, if you remember, and K1.Q is going to be Q being the closed string momenta, and which has the mass 0. So if we take alpha prime to 0, for this structure we get 1, and if we do, because the scaling of the mass, if you remember, this is important, I'm going to just go one step here. The scaling of the mass is k squared is 1 over alpha prime. Okay, the -1 here is not very important. We're taking the limit. And if we take this limit here, we're going to end up with 1. And if we take this limit, we're going to go to 0. So if we want to go to the proper alpha prime expansion of this, for the alpha prime goes to 0, we need alpha prime goes to 0, alpha prime k squared goes to 0, but not any k squared. We have to choose some specific one that in the expansion of the gamma function gives us a proper Q of t result, and for that we have to choose this downer version, and that's something that one of the most important things in the, at least in my opinion, in the paper, was that doing this, because this part, the finding effective field theory for massive string states is something that have been problematic because of this exact limit. Because when you take alpha prime to 0, masses go to infinite, so they decouple from the structure, the effective field theory that we have. Okay, so we choose this specific S, basically do our definition, you can always do that, and then do the expansion, the gamma function expansion of the alpha prime to 0, alpha prime k squared in this specific way goes to 0, 2. So doing that, we're going to end up with some, so if there is a kinematic inside all of these A, C, delta, E, and F. There's going to be kinematic stuff, because basically we are contracting partial X's and psi. So there is also polarizations inside these things. Let me also just, this is alpha is the polarization here, and epsilon polarization here. So there's going to be a structure of the polarization and momenta living inside these packages that we have here. And expanding the integrals and plugging back, we end up with this structure that you can see. There are kinematic packages, there are polarizations contracting with each other, momenta contracting with each other, and we end up with this term. Repackaging back to the field theory, meaning that for the polarizations, we plug back the fields associated with those polarizations, and for the momentas, plugging back the partial derivatives. What we have going to be as a result is going to be this term for the GM squared. And as you can see, it's a bit not, it should be red here. The problem is that what I showed you before for the GM squared. So this is the position that we're going to compare the string theory result and the biometric result. And the biometric result, this is exactly all of the terms, the same terms that they have here, and the relative factor is here is correct, but the problem is that the relative here, there is a numeric discrepancy. So if this here is true in the biometric case. And okay, also one can match the coupling constant, and the coupling constant is going to be, okay, also by dimension analysis, there are different ways to do that, but dimension analysis both give you the same result. This is the relation between the G string and the mass of the graviton, okay, mass of the massless state in the biometric theory, and also the relative mass of the Planck masses of the biometric. Okay, so now that was the GM squared. What about the M cube? Now, M cube is better in the sense that, okay, we know the state is open string. Again, it's 3 states, so we have 3 open string injected in our Riemann surfaces, and because of the fact we have 3 real variables, SL2C is sufficient, SL2R, sorry, is sufficient, and basically kills all of the integration variables. There is no integral, and what we have is going just basically doing some sort of contraction, weak contractions of it, and doing that weak contractions, we end up with these terms. Again, plugging back for the polarizations, the associated fields, and the momenta, the partial derivatives, we end up with this term. Again, we have all of the terms possible, so we have also the M cube. So if we could have matched, that's going to be the upshot of the paper, we could have read at least some of the information regarding the biometric, not full because we have only one equation, we had 4 variables. But we have this term, but the difference is that there is a 3 here, the relative factor between these 2 terms. This is 3, but in biometric gravity, it's 2. And it's coming from the kinematic structure of the Lagrangian in the biometric gravity. So the questions that can be asked, so what we see is the upshot is that the state that we chose and plugged back and did calculation for gives all of the terms structurally, but does not give the numerical structure that we have in the Lagrangian for the biometric gravity in the both cases of the M cube and GM squared. Now one can say, okay, maybe you should choose bosonic, maybe bosonic string theory changes something, yes, but to the worst, because we go instead of a 3, you get a 4. We did that calculation. That's what it is. Okay, now the next question. The whole discussion was that the biometric gravity is the unique theory that is ghost free. String theory is also ghost free. So does it mean there is a conflict here and something there is a problem? Again, the answer is no up to this order, because we are looking, okay, the ghost that we are looking at as a quadratic order, and the quadratic order, everything is fine. We still have the string theory, and the string theory is ghost free. Now the point is you should do a resummation of all the states in the tower, but at least up to this order, we don't have a problem with this, with the ghost. Okay, so I can now conclude. Basically, what we did, we looked at the 3 massive amplitudes of the open string and closed string. This is one of the things that has been done new in this paper, and we found somehow how to do the truncation. That's also one of the important. But when you're going to get from in the massive amplitudes, get to the effective action. We looked at the biometric gravity and tried to somehow manage it in such a way that one can compare it with string theory. And then we matched all possible terms, but the problem, there's an issue with the numerical factors. Now, again, we can look at other candidates, and the main candidate that one can look at is going to be in closed string. That's basically is the work in progress to see if we can basically choose the massive spin 2 from the closed string sector, which makes maybe, okay, one can in hindsight says, okay, the closed string started the massless, maybe we can choose it in the massive, but there are different ways to construct it, and we didn't want to go for the spin 4. Okay, that's, I'm just gonna go into the next paper. But this is something that is happening right now, and hopefully it's gonna be out soon. Okay, I think I'm, yes, finished. Thank you so much.
Thank you. Questions? May I ask a question? Is this truncation unique? Can you, I mean, you obviously you have tried to find it, so was it unique or you have possibilities?
So in this setup, in this specific setup, sorry, I can't move it again. No. So in this specific setup of this 3 amplitude, this limit is unique. So there is no other possibility. But one can try to ask this question that, oh, what happens if I have more massive states with different masses? Then that should be studied independently. And okay, just without doing anything extra, we looked at a bit of a step more. It seemed like in this setups of one massless and any massive, this seems to be just one route. There's a unique route, but that's I'm not 100% confident. But the point is here, it's yes for me.
Well, if no other questions, let's maybe stop here for today. Thank you, Pouria, again. Thanks to all speakers of today. And I remind you that we have this reception at 8 o'clock in front of the palace in Montero.